Alrighty. Hey, AP Chemistry. This is going to be our Unit 1 Important Information Part 7. We're going to be talking about valence electrons and ionization energy and connecting that to photoelectron spectra. Now, to start, I want to just share some answers to the free response questions from your previous homework. So if you want to pause and look at the answers here, here's the answer to question 1. And you could pause. Here's the answer to question 2. And if you have any questions or concerns, feel free to reach out or wonder why an answer is an answer. All right, so let's get into it. In our previous photoelectron spectra, we've identified this PES as a certain element that we know. The first peak, every time we look at a photoelectron spectra, just like this, the first peak is 1s, then 2s, then 2p, then 3s. It looks like this peak has a height of 1, 2. So this is 1s2. The next peak also has a height of 2. The height tells me the number of electrons. This next peak, the 2p, 6. 1, 2, 3, 4, 5, 6. Wonderful. And then 3s2. The element that has this electronic configuration, 2 plus 2 plus 6, which is 10, plus 2 more, that's 12 electrons, 12 protons then if it's neutral. This must be magnesium. All right, so something that's important to note here, each peak has its own energy, and I apologize that kind of like the x-axis here with the binding energy is kind of a little messed up, but assume all the way over here that we have 0, and then hundreds megajoules per mole is far on the left. I already wrote some notes here, so you could kind of copy along or get it down. Peaks further to the left require more energy to remove from the atom. These electron peaks, I really should say that. Each of these peaks correspond to electrons in the atom. More to the left require more energy to remove from the atom. That's because, I'm going to write this in a different color, because these are what we call core or inner shell electrons. So in this case, I'm going to highlight them in red and get in the habit of knowing that. This 1s peak is the closest to the nucleus. 2s is further away, but not as far as the 2p. These are all my core electrons. Core electrons right here. And then on the very, very end, and I'm going to use yellow for this, the electrons that are the furthest away from the nucleus on the outermost shell, we call those the valence electrons. It looks like this magnesium has 2 valence electrons. I'm going to use just black for that. 2 valence electrons for magnesium. We'll refer to that later. They're in the 3s. There's 2 of them in the 3rd energy level. That's the highest energy level. In a previous lecture, we've talked about that. I'm just quickly reviewing it here. So then, on that note, the energy required to remove electrons from each peak is called the ionization energy. And more on this definition later, but we've already kind of introduced this, right? Ionization energy is the energy required to move electrons, and each peak has its own ionization energy. So I'll see later that this 2s peak will have a specific energy to remove those electrons, and we'll say that those are the ionization energy of those electrons, okay? So each of these peaks have their own ionization energies. Each of these peaks require a different amount of energy, and we're going to try and tie together why this valence electron over here has less energy and why the core has more, and numbers connected to it. So let's look at some successive ionization energy. So I have a table here. This is going to be so important to AP exam. You have to be able to look at data as such and come up with a lot of information. So make sure you make like a beautiful note for yourself here. You have to be able to look at successive ionization energies, the energy required to move electrons. When I say successive, just to make sure, successive means next to or coming after. So like 1s, then 2s, then 2p, then 3s. That's what I mean by successive, that things come after each other. It might not be the same order. And what's also important to note, and put stars here for yourself, the first electrons removed require less energy. So if I start throwing some energy, H nu, I'm going to erase a little bit of that. If I just start throwing some energy, H nu, at an atom here, the first electrons that are going to be popping off are these valence electrons. And then once they are removed, then I have to go more on the inside, or I have to go with what's remaining and start removing core electrons. So let's look at how those numbers are going to play out here. So let's look at sodium. The ionization energy of the first electron that I get is 495. Not so bad. And then there is a huge jump here. Holy crap. When I start removing the second electron, it is almost 10 times the amount. Let's keep that in mind for sodium. Let's look at magnesium next. For magnesium, okay, to remove the first electron, 735. To remove a second electron, it's like a little double. It's not as bad. But then OMG, to remove a third electron, it is a huge jump. Almost 7 times as large. Let's look at aluminum, and I don't know if you can see what I'm doing here. To remove the first electron of aluminum, it's 580. To remove the second electron, it's like, okay, maybe 2 or 3 times larger. I would say it's not like that big of a jump. Then to remove the third electron, that's not even double. And then OMG, to remove a fourth electron, I have such a huge jump. OMG. Remember these huge jumps and what electrons they are on. Let's identify the huge jumps in silicon. The huge jump, let's see, 780 to 1, all the way over here. Holy crap. 4 times the amount of energy. For phosphorus, the huge jump happens over here with its 6th electron being removed. For sulfur, the 7th electron has a huge jump. And then chlorine doesn't really have any more huge jumps. It looks like it could have 7 electrons removed, and it's not so much of a huge jump. Now, why did I do all this? I'm going to say huge jump happens after 1 electron. For the second one, this is going to be after 2 electrons. For aluminum, after 3 electrons. For silicon, we're good for 4 until after the 4th electron. And then for phosphorus, after 5. Ooh, is this a trend that's happening on purpose? For sulfur, it'd be after 6. And then chlorine and argon, if I was able to get an 8th one, it might have a huge jump. But chlorine and argon, after 7. Let's put a pause on this for a second and go back to identifying group numbers and trying to connect something that we've talked about in class. These large jump in energies are removing core electrons. So let's keep that in mind. This red that I have highlighted here is when I first hit core electrons. Let's keep these numbers in mind when I'm going to put some group numbers in. So let's identify group numbers at first. This is group 1. This is group 2. So I'm doing a little trick here. So I'm kind of taking a little bit of an aside. In the middle here, we ignore the middle because these are our transition metals. So transition metals, blech. I'm just going to say we don't really number them. They don't have a nice trend. So we ignore them for now. So I skipped this middle group. I'm going to say my third group is over here with boron, then carbon, 5, 6, 7, 8. I've seen this order before. Let's look back up at sodium. There's a huge jump after 1 electron. Sodium's in group 1. For magnesium, there's a huge jump in energy after a 2nd electron. Magnesium is in group 2. Do you see what I'm getting at here? For aluminum, there's a huge jump after 3 electrons. Aluminum's in group 3. You'd guess it, going all the way to silicon, group 4 after 4 electrons removed, group 5 after 5 electrons removed. Guess what these group numbers represent for these elements? These things that I've highlighted here in my successive ionization energies, looks like phosphorus has 5, sulfur has 6. These are valence electrons. Your group number is equal to the total number of valence electrons for that element. Know this. You need this for the end of Unit 1 here, and you need this for the beginning of Unit 2. OMG, this is beautiful. And it is nice to help you remind yourself like how many valence electrons each element has. From now on, we could see with this little trick that the group number is equal to the total number of valence electrons. What you'll also know is elements in the same group will have the same number of valence electrons. Let's write that down as an important note for ourselves here. I'm going to kind of put a little blue wave around this. So important for you. Elements in the same group will have the same number of valence electrons. So if I'm ever given successive ionization energy data, I try and find that jump, that OMG. That jump means I've hit core electrons. So I'm going to write that in red here. Huge jump means I've hit core electrons. And any other electron before that is the valence electrons. And elements in the same group will have the same number of valence electrons. So if I get a huge jump, let's say I didn't know this was magnesium. I'm going to block this. And I was given this these ionization energies. There are possible answers. This could be Be, this could be Mg, this could be Ca. All of those elements would have 2 valence electrons because they're in the same group. Let's end with looking at one AP style question, and then I'd like you to try the last AP style question on your own. It's a little bit tougher, but having to remember charges. So let's look at this first one. Based on the ionization energies of element X given in the table, it should say at left here, which of the following is most likely the empirical formula of an oxide? So remember, oxide has a 2- charge. Okay, so if I look at these energies here, I'm going to highlight them. Okay, my first one is 577, and then my second one is like a little bit higher, not so bad. My third one is a little bit of a jump, right? So the first one, maybe 3 times larger. By the third one, it's like not even 2 times as large. It's like maybe 1 and a little change. And then OMG, 5 times as large here. OMG, jump. That means I've hit core electrons here. This means this element has 3 valence electrons. What elements would have 3 valence electrons? Writing this down here. Well, that's anyone in group 3. So group 3. So that would be aluminum, you could do boron, you could do gallium. These are just examples. From our summer work, you need to remember that elements in group 3 form a +3 charge. So let's just do aluminum and oxygen because it wants an oxide. Aluminum is in group 3. It typically forms a +3 charge. Oxygen's -2. We could do that handy-dandy crisscross method to figure out the formula, Al2O3. If Al was equal to our unknown X, that means the correct answer would be C, X2O3. All right, so This is very important information for us. This is going to help us, but these are sample AP style questions, like ripped right from the AP exam. For evidence of this, I'd like you to make sure that you could answer this last AP style question on your own. Make sure you answer it in similar wording to the previous one, but just different energies. Try and use our knowledge here to answer this last question. Also, choice B should be X little 3. I guess the subscript didn't go there, so I apologize. Alrighty, that is all. This is valence electrons and ionization energies.